We are in AP Calculus. So today's date is Friday, February 7th, 2/7, 2020. We are doing our last lesson for this unit, approximating average value. Claire, what are we doing today?
We are interpreting average value and using a trapezoid sum to approximate area under a curve.
There it is. So we're just adding on one additional type of approximation for an integral, and it is the most accurate. So it's also the hardest, right? You get more complex and more accurate. So total change versus average value. What we've been dealing with thus far in 9.1 and 9.2 is just talking about your total change. We haven't ever talked about average value yet in this lesson. We've talked about it before in previous units though, so it should be like, hey, we've done this before. So here's a table. We have time and R. Something is happening in inches per hour. Maybe rain is accumulating over something. I don't know. Maybe it's a snail going all along at a pace of 1 inch per hour. Don't know. But there it is. What is the total change? You should know this. Total change is just the...
The integral of A to B.
Integral from A to B. So if I... let's just choose an A and B. What do you want your A and B to be, Claire?
2 and 12. No, sorry, 0 to 7. Oh, God.
You're good. 0 to 7. We just randomly chose those, by the way. Of your, what are we doing here? Capital R, right? R of t dt. That is the total change. And then we can actually calculate that. I don't know what it would be. It's some number. All right, some number.
Wouldn't it be 10, though?
Well, we don't know what the function is. We only have a table. We have incomplete data. You can't assume. That's the main thing from lesson 9-1, right? We don't know what's happening there for the actual integral. We could approximate it using a left Riemann sum, and then we have to do a bit of math, or using a different type of Riemann sum. But there it is. So total change is just an integral. But average value, and you've seen this before, looks like this. It's the same integral between 0 and 7 of capital R of t, but with a twist. Does anyone remember what that twist is?
It's divided by 7 minus 0.
Divided by 7 minus 0. That's the only difference. And sometimes I'll write that 7 minus 0 out front. I'll do like 1 over 7 minus 0. That's the same thing as writing divided by 7 minus 0. So both the same form. Yeah, so average value of f. And we have to assume here also that f is a rate. I'll make that note here. This has to be a rate. I can't just say f is some sort of, I don't know, some amount. It's a rate. So from A to B, and we just write exactly the same thing down, but instead of 0 to 7, we say A and B. So we'll say this is now the integral from A to B of capital R of t dt. All of that divided by... Oh, I was copying it down too verbatim. Yeah, log it. F of t dt all over b minus a. And again, I told you that I can sometimes write this 1 over b minus a. The integral, the same thing from a to b of capital F of t dt. They're the same formula. So that's the only new thing that I'm going to be teaching you so far. Let's review left, right, and midpoint sum, and then I'll teach you the last new thing, which is trapezoidal sum. So there are 4 ways that we in AP Calculus, AB and BC, will approximate integrals. I'm trying to think, in BC, do you ever do anything weird? Those are the only ones that I've ever learned, so I'm assuming that's all we're going to learn. Left sum. So if I have, I don't know, some numbers, I'm going to make up A, B for some general values. If this is the height of A, this is going to be f of A. So this is just a fancy way of saying this is the y value of A, or this is the height at A. So a left sum has this shape, this Tetris block piece with a tail on the left. Interesting note, what do I not use in this table when I'm doing a left sum?
The very last
Yeah. That top or that bottom right. So let's just go ahead and make some random points here. We'll do some sort of increasing function. Point, 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 point. If those are my points, maybe I can draw the same points over here and here again. Do I go an integral that goes out this direction, or sorry, a bar that goes out to the right, or a bar that goes out to the left?
Start with the leftmost.
You start with the leftmost point and go out to the right. So it's kind of counterintuitive, but use the leftmost point, and that is the way to memorize that. Use the leftmost point, and I'll write here, leftmost point. Perfect. And then again, our formula to figure out what this area is, since we don't have a graph, I do b minus that a, and then I multiply by f of a. So it's b minus a times the quantity of f of a. And this is just kind of like your base of your rectangle. So all right, that's your base of your rectangle, and then this is your height of the rectangle. All right, let's show a right Riemann sum. Let's do a general a and b again. A, b, and then this is going to be f of a. Nope, no, that's not what I'm using. I'm using under f of b. I don't care about f of a. In fact, that first, like, farthest left coordinate, the height of a, we don't use him. Just cross him out. We never will use him in the right sum. And then let's go ahead and draw a graph. Draw roughly the same dots, or any dots for that matter. It doesn't really matter. Some dots, and I use the rightmost point. So right here, rightmost point.
Go left.
So I go left.
That's kind of confusing.
Definitely.
Like the right sum, you go left, and the left sum, you go right.
And the under approximate is when it's
Over.
increasing.
Yeah, there's lots of opposites. That's why, and I get confused with the same thing. So you're not alone. If you ever get confused, then draw out a graph. Just from a random pen here. Cool. Midpoint sum. So we need a bunch of data for this one. So if I have an A, a B, and a C, which height do we care about?
A and C.
F of B.
We care about f of B. Yeah. In fact, what things do we not care about at all on this graph or in this table? We don't care about that one, or that one, and we don't care about B, or I guess this would be D. So those are a bunch of values we don't use. And yet, even though we're using less data, it's more accurate, which is kind of interesting, right? Although, I bet I could design a function where midpoint sum is really, really, really inaccurate if I have some sort of cool sine wave where we choose these bounds in the worst possible way. Anywho, let's go ahead and show what's happening here. Draw at least a few points here. So a point, a point, a point, and a point. So a midpoint sum, I'm going to say that that's my middle right there. So in between those first two, I'm going to go make a rectangle right here. So where this is my A, B, and C. My A and B up here are A and B, A and B. And to find the area of that one, I do what? What's my formula?
E minus A times F of B.
There it is, times f of b. Perfect. So that's all of your review. So now it's time for the infamous trapezoidal sum. These all happen roughly equally. I would say left and right most sums happen a little bit more frequently than the others, but they're pretty all equal. I would say maybe the least popular is midpoint sum. But yeah, know all these pretty well. So for this one, we need to know A, we need to know B, we need to know f of A, and we need to know f of B. And the cool thing about this thing, well, maybe not cool if you don't like work, is you have to use every single value. There's nothing crossed off. There's no x's. Every single one of these values in this table we're going to be using, which means we're going to get a really accurate number, theoretically, right? So I'll write a note here, use all. There's no x's for here and here. So what's happening? I'm choosing my A and B. Let's just choose them kind of randomly here. Let's say that's my A, that's my B. And I'm going to make a point, I don't know, here. And if it's here, that's kind of too simple. Let's make one that's slightly raised to like up here. What we're going to do is we're going to connect these with a straight line. So I have a line tool. I should be using that. Reconnect it with a straight line. Which means if our function is curvy, that it's not a perfect approximation. I have some sort of curve that's happening there, but it's better than what happens if I just do a giant staircase. So I have my line, and let's go ahead and make our lines go straight down. So that is the area of not a rectangle anymore. These rectangle formulas were nice and easy. Base times height, base times height, base times height. This is now a trapezoid.
So you have to do
What's the formula for a trapezoid?
minus A times f of A plus 1/2 B minus A times
There's a
B minus A.
No. Okay, so
I don't know the trapezoid formula, but
everyone write a trapezoid out here to the side. I'm going to do two directions. So the normal trapezoid formula that we have looks like this, where we call this one base 1 and base 2, and then the formula says, oh, and we also need a height that's at a right angle, so I'm going to call that my h. We say, I need to find the average of the bases. Base 1, base 2, divide by 2. That's the average of the bases. So base 1 plus base 2, all of that divided by 2. That's the average base times the height. That's the formula. Average bases times the height. But the unfortunate thing for us is this trapezoid is turned on its side. So our base 1 is right there, and our base 2 is right there. So this height of base 2, that's the same thing as saying f of b. This height of b is this distance right here of base 2, and then b1 right here, that's f of a.
So then it's f of a plus f of b divided by 2
Yeah.
times
And this height here
minus a.
is the same thing as the difference between b and a, or just b minus a. So I plug those into my formula, and then we have our answer. Our formula should say f of a plus, we're taking the average of the bases, plus f of b, adding those together, divide by 2, and then multiply by the height, which is times b minus a. Times, I don't have very much room, b minus a. And please make a note either here that this is the average, or here that this is the average, these average values. So whenever I'm doing my table, the general way you're going to annotate your table and say, okay, if this number was, I don't know, 7 and this number was 11, what's the average of 7 and 11? Well, we add them together. 7 plus 11 is 18, then divide by 2. The average of 7 and 11 is 9. I'll put a 9 in between them to let myself know, hey, I've taken the average and I just need to multiply it by whatever the difference is between those x values or t values or wherever they are. Cool. And I'm realizing maybe for next year I should probably put at least one example. I have all this room over here. But that's the end of the lesson for today.